Buenos dias. Today we're going to be looking at modes of vibration. There's lots of applications for this. Some of them are a lot of mechanical systems. You want to study how different things vibrate. Even chemistry, look at modes of vibration of different molecules. We're going to focus primarily on that which is applied to musical instruments. Many of you play musical instruments. And we're going to be looking at strings, open pipes, and closed pipes. So when it comes to the instruments, if you play a stringed instrument, orchestral instrument, guitar, piano, it's really the string that's vibrating. That's what we're talking about. For the wind instruments, flute, clarinet, trumpet, those types of instruments, we're really looking at how the column of air inside it is vibrating. So one's looking at a string, the other is looking at a column of air. But we're going to look at those, and the way that you look at that, the way we analyze these systems is similar for other types of systems that we won't be looking at. Like, for example, if you play the marimba, that's not a bar. It is a bar. It's not a string. It's not a column of air. And bars, they vibrate differently. But the method of analysis that we're going to use is similar to those. So once you understand this method, you can look at other mechanical systems. You can look at other types of instruments. So let's get started. Really what we're looking at is we're looking at a standing wave. And so when we look at a standing wave, for example, at one instant the wave might look like this. And then when you have resonance sometime later, it might look like this. And we have a standing wave. And then what we refer to is these, if you remember, these locations are the nodes, okay? And then the locations here, these locations with large amplitudes are the antinodes. Put A's here. So nodes and antinodes. And the key thing you want to know is we're going to refer to a segment. A segment goes from a node to the next node. That is half of a wavelength, because if you follow the red one, okay, that's a complete wavelength covering node to a second node to a third one. That would be a full wavelength. Same thing with the green. Okay, follow that. That would be a full wavelength. So therefore, one entire segment is half of a wavelength. That's the key piece of information. If you got that part, everything else will fall into place. Okay, so when we look at a string, the key for a string is that it's fixed at both ends. On a guitar, we call it the nut at one end and the bridge at the other. And that is a node at each end. That's the key. It's node at each end. And that's the criterion. It can vibrate in different modes that all have, what they have in common is they each have a node at each end. So we're going to look at a simulation here. And this simulation, and you can see a green line. This is representing something fixed at both ends. And this is what we call our fundamental frequency. And this is what happens when you pluck a guitar string or a violin string, it's going to vibrate like this back and forth. It's fixed at both ends. Okay, and this is called the fundamental. It's a lowest frequency. It's also referred to as the first harmonic. Okay, now, but this is not the only way that it vibrates. It actually it vibrates lots of different ways all at the same time. And that's what gives each instrument a different timbre, is the different mixture of these different harmonics. So let's take a look at another harmonic that has, it's got to have nodes at each end. Okay, so this is another mode of vibration. Okay, that would be the second harmonic, and then the third harmonic, and the fourth. And so hopefully you're seeing the pattern here, that basically the first harmonic has one big segment, the second harmonic has two segments, the third harmonic has three segments. Okay. Now, so we're going to fill out a chart, and this chart is going to be really helpful when it comes for you to do the problems. Okay, so this chart is unending, so you're going to see a pattern, and then it doesn't stop. Okay, so the first mode is what we call the first harmonic. And the diagram looks like this. And we simply say, oh, this is a string of length L. From node to node is length L. And if length L in this diagram, that's half of a wavelength, then we say that L equals lambda 1 over 2. That is the wavelength of the first harmonic, half of that. First wavelength divided by 2 is equal to the length. Now, the second harmonic, same length string, looks like this. The wavelength has gotten smaller. It's not the same wavelength. It's the same length of the string. L is the same, but the wavelength has gotten smaller. Okay, so now what we have is that length is lambda 2. So if you were to solve for lambda in the first one, multiply both sides by 2, lambda 1 is 2L, but lambda 2 is just L. Okay, so the first harmonic has a lower frequency and a larger wavelength than the second. And then the third mode of vibration, that's the third harmonic, and it's 3 segments. And each L is equal to lambda 3. And you say, well, how many segments are there? There's 3 segments. Okay, so if there are 3 segments and each one is half of a wavelength, we see it's 3 lambda 3 over 2. And then the fourth one, it would look like this. And we would get, you could, if you want to see a pattern here, this is 1 lambda 1 over 2. This would be 2 lambda 2 over 2, which reduces to the 2's cancel and you just get lambda over 2. This is 3 lambda 3 over 2. This would be 4 lambda 4 over 2, or we can just say 2 lambda over 4. Now, sometimes you're going to take this equation and solve for L. Sometimes you're going to take this equation and solve for lambda. The key is to start with this equation, whatever equation you're dealing with, and then solve for the variable that you need. Okay? So this is for a string. Now, we could continue this on to whatever harmonic you have, and the basic form would be L would be equal to n lambda n over 2. So if you wanted the 11th harmonic, it would be 11 lambda over 2. That's how it goes. It's pretty simple, goes straight forward. Okay. Now, let's go to an open pipe. An open pipe is open at both ends. And once again, we're looking at the vibration of the column of air, not the pipe itself. We're not hitting the pipe to make the pipe resonate. We're making the air inside it resonate. And the key for this is it has an antinode at each end. Okay, so that's the key. We're going to say it has a length L and it has an antinode at each end. So now let's go to our simulation and let's look at open at 2 ends. So this is our first harmonic. It is open at both ends. It's got an antinode at each end. It's got a node in the middle. Okay. The next one looks like this. And as such, what's common about all of these is they all have an antinode at each end. Okay. And notice that as you go to the higher harmonics, the frequency changes, the wavelength changes, the wavelength gets smaller, the frequency gets higher, but the product of the frequency and the wavelength remains constant because that's the speed of the wave. Speed of the wave is determined by the medium. So now let's go to the chart and let's see if we can figure out how this works on the chart. So what we get is we get the first harmonic. The diagram looks like this. It's an antinode at each end. Well, you might recognize that the left-hand side of this diagram is half of a segment, and the right-hand side is half of a segment. So really together, if you were to switch the sides, it would look like this. Okay? But it's got the node in the middle. So this still is lambda 1 over 2. When you go to the second harmonic, the diagram looks like this. The left side is a quarter of a wavelength. The right side is a quarter. 2 quarters make a half. And there's one segment in the middle, which is another half. So this is lambda 2. And the third one would look like this. It's got a quarter on each end and then a full wavelength in the middle. So it would be 3 lambda 3 over 2. And you might look at this and say, well, gosh, the formulas look exactly the same as the string. And yes, they are. They're the exact same formula. So we could say the pattern is n lambda n over 2. Okay, if you want the 11th harmonic, it'd be 11 lambda over 2. That's how we get it. Sometimes, once again, you're solving for lambda. Sometimes you're solving for L. Both L and the length and the wavelength will be measured with the same units. Inches, feet, meters, centimeters. Just need to be consistent. Okay? But you'll notice the formulas look identical. The reason they're identical is because we have symmetry. We have nodes on the same thing on each end, nodes on each end, and on the open pipe, antinodes on each end. Well, now it's going to get more complicated because now we're going to look at a closed pipe. And a closed pipe is a pipe that is closed at one end and open at the other. So it's going to have a node at one end and an antinode at the other. So now we have asymmetry, and this asymmetry is going to result in something different, but our analysis is going to be the same. So let's go back to the simulation and let's look at a system like this. Okay? So notice we have a node on the left and antinode at the right. This is the fundamental. But now what we get is this here. The next harmonic that we hear is not the second harmonic, it's the third one. Okay? Because it's going to be 3 times the frequency. And then we're going to have 5 times the frequency. So what we're actually getting is the odd harmonics. We're not getting 1, 2, 3, 4, the integer ones. We're getting the odd integers. Okay. So let's sketch these and show you how we get the formula from them. So what we get, the fundamental is referred to as the first harmonic. That's always the case. The diagram would look like this. That is simply half of a segment, or it's a quarter of a wavelength. So we say that lambda is lambda 1 over 4. It's a quarter of a wavelength. So if you want to find L, it's lambda over 4. If you want to find lambda, it's 4 times L. So the wavelength is actually 4 times the length of the pipe. You actually have a wavelength that's longer than the pipe that it's resonating in. So only a quarter of the wavelength is actually in the pipe. Now, the next mode of vibration is not the second harmonic, which would be twice the frequency, half the wavelength. The next one is actually the third harmonic. And it looks like this. It's a quarter on the right in this case and a half, so that would be 3/4. So L, that's going to be 3 lambda 3 over 4. Okay, so it's 3/4. If you want to solve for lambda, you take the length of your pipe, you multiply by 4, you divide by 3, that gives you the wavelength. You don't get the fourth harmonic. It doesn't resonate in that pipe because you'd have to have symmetry. But we do get the fifth harmonic. Remember, the length of the pipe is the same. Okay, still a length of pipe L, but different modes of vibration all at the same time. Okay? And so when we do this, we say, oh, here we have half of a wavelength, and another half, that's a full wavelength, plus a quarter. That's 1 wavelength and a quarter, or 5/4 of a wavelength. And that would be the length. So what you're going to see here is that the general form we get is the harmonics are going to be n, lambda n over 4. However, you only get the odd ones. Okay, so we only get the odd ones. You won't get the second harmonic. You won't get the fourth harmonic. We only get the odd ones in that. Okay, so those are the 3 types of pipes. So you want to have this chart. know how to use this chart, draw the diagrams, use the formulas, because that's going to be really helpful in the problems. Now, let's take a look at the concept builder. I've asked you to do some of the concept builders, and let's see if we can get this to kind of show you what's going to happen here. Okay, so what you have a string. So the first thing to remember, we have a string. Has a length of 40 centimeters. So we have a string of length 40 centimeters. Identify the standing wave pattern for the harmonic that has a wavelength of 80 centimeters. Now, if the wavelength is 80 centimeters, then half of a wavelength would be 40 centimeters. Now, half a wavelength is one segment. Remember that. Always got to remember, half of a wavelength will be one segment. And so since we look at the 80 centimeters and say half of a wavelength is 40, and our string is 40, oh, well, that means the thing must just have one segment. Okay, so that's how that one goes. You look at there. Okay, now let's take a look at one for an open pipe. Okay, so this is, it says here in this problem, an open end air column has a length of 64 centimeters. Identify the standing wave pattern for the harmonic that has a wavelength of 32. Now, if the wavelength is 32, that means half of a wavelength is 16. Okay, half of a wavelength is 16. Now, if half of a wavelength is 16, but the column is 64, that means there must be 4 half wavelengths, 4 16s fit into the 64. So what we've got to do is we've got to find one that has 4 segments, but you don't want to be confused here. You say, oh, this one's got 4 segments, 1, 2, 3, 4. Well, there's a quarter on each end. This one really has 5 segments. We're looking for one with 4 segments. This one has 1 segment in the middle and then 2 half segments. So this has really got 2 segments. This one has 3 segments. That one's got 1 segment. We want 4 segments. Here it is. There's 1, 2, 3, and then the 2 half ones on the end. That would be 4 segments. Excellent. And then we're going to look at one with a closed end. So this one can be a little bit tricky sometimes. Okay, so what we have is we have a closed end air column, has a length of 25 centimeters. Identify the standing wave pattern for a harmonic that has a wavelength of 20 centimeters. So the wavelength is 20 centimeters. That means half of a wavelength must be 10 centimeters. Well, how many half wavelengths can fit in a 25 centimeter pipe? Well, that would be 2.5. Okay, 2.5 segments. Okay, so let's take a look. We know that each segment is half a wavelength, and since the wavelength is 20, each segment must be 10 centimeters. So if this one would be 10, 20, 30. Well, we don't want 30, we want 25. This would be 10 and 5. That would be 15. We don't want that one. This would be 10, 20, 35. We don't want that one. This would be 10. That would be 20. We don't want that one. There's one segment is 10. Another segment is 20. Half of a segment would be 25. That's what we want. And we're good to go. Okay. So I hope this helps you. The key is to have the diagram. I'll leave the diagram here on OneNote. You want to see the pattern, and then of course we'll be using the wave equation with this to solve some of the problems. So I've done some sample problems for you. Should be ready to go.